Welcome back. We're going to continue our investigation of Chapter 20 by now looking at the other type of connection that we're going to deal with called parallel. Now, today we did a bunch of sample problems based on series connections. We're going to look at the other side called parallel. But before we do that, we want to go back and re-look at the difference between EMF and terminal voltage. Now, like I told you before, really for our purposes, we are going to have to know the difference between the two. But I feel obligated to give you at least a little foundation behind it so that should you come up across it again, you'll know why. Okay, and we said that the EMF was the total amount of energy, per charge of the circuit. And terminal voltage, which we'll write VBA, or VAB, just know that it's V, is going to be the energy used outside of our battery or other voltage source. Okay? Well, the reason why that the EMF is always bigger than the terminal voltage is because there is a certain amount of energy needed to move those charges inside of the battery itself. Okay? And that is what's called internal resistance of the cell. Every cell will have some resistance to it that's going to take a little bit of energy in order to create that potential difference on the outside that we can use. And so EMF is always going to be larger than the terminal voltage. And I didn't give you the equation yesterday because I wanted to wait for it today. But if we wanted to find out what the actual terminal voltage is, so VBA or whatever, this is our terminal voltage, as voltage between points A and B in a circuit, is going to equal the EMF, the total energy, minus the current flowing through times the internal resistance of that cell. And this is our internal resistance. And that I is obviously our total current. EMF is the total energy. And we're actually going to get an opportunity. If we get the opportunity to do this lab, we'll do a lamp lab. And I'll have you playing around with the 9-volt batteries. And before we do the lab, I'll actually have you determine what the voltage of the battery is when nothing's running through it. And it should be right around 9 volts, maybe 8.8, 8.7, depending on the age of the batteries. Okay? But then when we hook them up to the lamps, we're going to find out that that voltage is going to be less. And that's because some of the internal resistance takes some of that EMF, some of that energy per charge, and we have to use it inside the cell itself. This is what happens when your batteries die. It's not that they can't create that voltage, it's just they can't create it fast enough to use because the internal resistance becomes large enough that you don't get a large enough terminal voltage in order to run your device. If you let it go and let it sit on its own by it for a while, that EMF will build up enough again so your thing can use it, the battery will still be able to be used for a little bit. And we'll talk about that in more detail. But for now, let's look at the next character, the next combination of how we're going to hook up our resistors. And these are called resistors in parallel. And we're going to start off by drawing our diagram again. And we're going to once again have our total voltage. Okay, so here's our V total. But now we're going to come up and now my current is going to split. It's going to split into 3 different sections. I'm going to do a resistor here, a resistor here, a resistor here, and they'll have them all come back together. Boom. And then come out and come back around. Once again, I'll put my ammeter, I'll put that in right here. I'll put an ammeter in to measure the total current. Okay. But I'm also going to put an ammeter here. I'm going to put an ammeter here. I'm going to put an ammeter here in order to measure the current through any one of the individual ones. And I'm going to label this, we're going to call this R1 and R2 and R3. So just like before, okay? But now when our current comes up, and actually let me erase this and kind of clean this up just a touch because I don't want anybody to freak out and go, oh, they didn't, da-da-da. So let me put this here and we'll redraw this. We'll have it come in like that because that seems to make people happier, okay? This part right here is called a junction. And it's a spot where 3 or more lines all come together. And so what happens is the current comes up and it's given a choice. And so let me put this in. We have our current leaving the battery. Once again, it's our I total. And I total comes up through. But now when it gets to that junction, it's going to split. And some of that current's going to come up through here and just go through R1. So that'll be I1. Some of the current will go through here. That'll be I2. And some of the current's going to come down and go down through here. And that will be I3. Okay, so this is our basics. And we're going to put our voltmeters in here in a second. Okay, but what makes the parallel connection different is that if we have a break in any one of these paths, like if we take out R3, it doesn't change R1 and R2. Current will still continue to flow through them. This is different than series, where if we took out R3 when we're in series, the entire circuit would go dead because now there's a break there. Here, we still have our complete loops in R1 and R2, even though R3 might be gone or turned off for that matter. So that's the difference between parallel and series. Okay? So the key with parallel, and the first characteristic, is that these devices all operate at the same voltage, also all operate at the same voltage. Okay? And so this is all based off the law of conservation of energy. It doesn't matter when you, remember, if you leave your battery, you're going to gain a certain amount of voltage. When you come back around to that other end of the battery, you will have lost all that voltage. So it doesn't matter if you go through R1. So let's say you gain, I'm going to do 9 volts. Let's say we do 9 volts when we go across the battery and gain it. If you go through R1 and come around, you have lost 9 volts. But wait. What if instead you go through R2? You gain 9 volts going across the battery, go across to R2 and come back around? You still have lost 9 volts. And so because they connect the same points, the voltage drop across each of them, and I'll draw this in. So if I were to put in a, oops, hang on, put it in green, a V1 here, a V2 here, I know it's tight, I should have made it a little bit bigger, and a V3, you may want to readjust yours, make it so it's bigger so it's easier to see, okay? But though those voltages have to be the same because they all connect the same all those connect the same points. And so we can say that the total voltage must equal V1, which must equal V2, which must equal V3, and which must equal ... however many more we have. And again, this is based off the law of conservation of energy. It doesn't matter what path you take. You are always going to be losing the same amount of energy because you still get to point A to point B. It's like if you start here, okay, and you want to get down to the gym. It doesn't matter if you go out the door and turn left and go down those stairs, or you go down and turn right, go down those stairs, you still lose. You're still going to get to the gym regardless of the path you take. You're still going to lose the same amount of potential energy. Or if we, jump out the window to get down there, you'd still lose the same amount regardless of the path. So the same thing works here. So that's first and foremost. The V total is equal to V1 is equal to V2 is equal to V3. Now, the second one is based off of Ohm's law again. And the fact that Ohm's law states that the amount of current is inversely proportional to the resistance. Okay? So the larger the resistance, the less current goes through. And so if we come up here and look back at our diagram, if R2 is bigger than R1, it will have less charges, less current going through it. And I'll give you an example tomorrow using the cafeteria. Okay? Remind me to use the cafeteria example. If I forget it, somebody mention it to me. Okay? To try and explain that and give you some idea. But even though the energy drops will be the same, different resistances will let different amounts of current go through. Okay? And so this is based off of Ohm's law. Okay? The third one is based off law of conservation of charge and the fact that we talked about that junction, how that junction's there. That if you, whatever current you have coming in, I total, actually this should be in red, I apologize for that. That should be in red. But our I total must equal I1 plus I2 plus I3 plus ... Okay? And this is based off of the law of conservation of charge. No charges are lost. So if I scroll back up to our diagram, when my total current comes up and it hits this junction, hits this spot right here, this junction, it splits. Some is going to go through I1. Some is going to go through I2. Now again, if R2 is bigger than R1, then the current going through the first one will be more than the current going through the second one. Whatever's left over has to go through I3. But if you add them all up, no charges are lost. So the total current must be equal to the sum of the individuals. Yep. The last one has to deal with how we can find out that total resistance. And this is a derivation, okay? This is all based off of, I'm gonna put this in black, but it's all based off of the fact that the resistance is inversely proportional to the area. We've already discussed this. And so every time you add a resistor in parallel, you in essence are making the total area of my total resistance bigger. And so in essence, my total resistance is going to go down. Now let me prove to you this through the derivation. Derivation is this. We know that V total, sorry, let me go back, let's start with this. That I total is equal to I1 is equal, plus I2 plus I3. Okay, that's what we just got done proving. We also know that I equals V over R. And so I can replace I total, I'll keep this in green, with V total over R total. And I1 is V1 over R1. And I2 is V2 over R2. And I3, V3 over R3, plus ... Okay? So the other thing I want you to remember and keep in mind is that V total is equal to V1, is equal to V2, is equal to V3. And so if I divide through, since they're all the same, these are all going to cancel each other out. And so we end up getting that 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... Okay? And again, so what we're saying here is it's an inverse relationship. As you add resistors in parallel, the total resistance goes down. Now, it seems a little weird. I add a resistor, and now the total went down, but that's what actually happens, and we'll prove this in a lab. So tomorrow, we will do some sample problems with all these and analyze them again. Once again, key thing to remember, subscripts are key. Okay, you have to remember to keep all the subscripts the same. Okay, so everybody have a great night. We'll practice this tomorrow. We'll see you later. Bye.